documentation such as this roadmap. And there's a manual for Red System which has become quite long in the past half year. Each time features are added, the manual is also extended. So there's really, relatively compared to other very young projects, the documentation for Red is already very good. And I'm not spending a lot of time on that. So here's the planning. Here's the bootstrapping plan to bootstrap Red System to Red. And green notifies the parts that have already been done. So you can see that Red System is basically finished, although it's still being enhanced as it is being used to build Red. That's very nice. If during the development of a platform you also use it to build stuff, you get a very good idea of what works and what doesn't work very well. So as Red is being developed in Red System, Red System is continuously being enhanced with that new experience. And you can see it grow at least week by week and often day by day or even hour by hour. It's really nice, the speed of the project. So you can see that Red System is basically done, although it's still being enhanced. The next phase is to write Red, the higher level language. And the memory management has been written now. And from the experience writing the memory management in Red System, Red System is being enhanced. And that's very nice for me because all the time the enhancements are things that I can also use in making bindings. So I'm doing quite different things from Nenad, but the enhancements in Red Systems can be used by me as well. So they're very welcome. And what you would usually see in the development of another language is that the compiler and the runtime library for a new language are usually written in C. And the nice thing about developing Red System first is that the runtime libraries and the Red compiler, the runtime system is written in Red System instead of in C. And because it is being bootstrapped in Rebel 2, the compiler can be written in Rebel. And so the next step, first we need the Red System runtime, which is now being worked on. The Red runtime written in Red System, it's a bit confusing. And after that, the Red compiler can be built on top of that. And the Red compiler is probably going to generate Red System code. The original plan was to have it generate machine code directly, but it will probably be efficient enough to make it generate Red System code. So the system is really being bootstrapped upon itself in a very nice way. That also means that it takes a bit longer to get to the eventual goal. And so after the runtime, the Red compiler must be written, and the Red compiler will be written in Rebel. But when you have Red, you can go back and then recompile your Red System compiler in Red instead of Rebel, and you can compile your Red compiler in Red instead of Rebel. And that's the next phase, that's called the rewrite here. First rewrite the Red System compiler, then the Red compiler, and after those two first rewriting phases, Red will run in Red. And because in the past half year we made Red System to run on Syllable Desktop, Red will also run on Syllable Desktop because it is built on Red System. And then when you can rewrite Red itself in Red, then you have lost Rebel. And that means that at that point, after step 2 here, Red will run on Syllable Desktop. So at that point you will be able to compile Red programs on Syllable Desktop, and you will also be able to compile them for Linux, so for example for Syllable Server, and for Windows, and for macOS, and for the other backends that we have by then. So probably for ARM, and for Android you need an ARM CPU backend, but also a lot of platform support for ARM. And there are two ways to do it. If you target Android, the usual Android applications are Java programs that run in Google's own Dalvik virtual machine. So Red has two ways to run on Android, and I don't know which way will be chosen. You could generate ARM code that would run on Android directly on the Android operating system, which is Linux. So because you already have all the Linux support, if you have ARM support and some extra Android runtime, you can compile directly to Android, to ARM. But the other possible way to do it is not to generate ARM machine code, but to generate bytecode for the Dalvik virtual machine. And then Android thinks that you are running a Java program, but you're actually running a Red program in Dalvik bytecode. And if you do it that way, it will be much easier to port, to bind to all the Java libraries that are in Android. Android is mainly a Java system. And that means that the system libraries and the system interfaces are in the first place in Java. And lately Google has been adding some low-level C interfaces so that you can now get at the same functionality from C and C++ programs. But the basic operating system platform on top of Linux is written in Java. So if you generate Dalvik bytecode from Red, you will be running in the Dalvik virtual machine, and that is the exact place where you can easily bind to the Java libraries that constitute the Android upper layer system.
Why should an Android developer use Red instead of their own Android tools?
Well, we'll see. But the whole point about Rebel is that Rebel is quite special. It's actually so special that we have learned in the past years that most people don't understand it. So that's a problem and an advantage at the same time. It is quite unique, so it has unique advantages. But on the other hand, most people don't get the advantages. So these days most people program in Java and .NET, similar languages, and that's why Android is mostly Java on their own Dalvik virtual machine. So in the first place, the public for Red will be Rebel people who already understand the Rebel advantages, but maybe want Rebel in an open source form. I haven't even said that yet, but Red is open source, and compared to other Rebel inspired languages such as Boron, it has a very liberal license. Boron is under the LGPL license, which is entirely okay for Syllable, but Red is under the BSD license. So there's more that you are allowed to do with Red than with Boron. And that makes it suitable for applications, because Syllable is mainly under the LGPL. I've said before, people think of Syllable as a GPL system, but most of the code is under the LGPL. That is important because our libraries are LGPL, and that means that you can build commercial closed programs on it. We think that an operating system should be a platform for both open source and closed applications. So that is no problem if the operating system has LGPL libraries, because you will, if someone makes a closed program for Syllable, such as Rebel 3, we just run the closed program on Syllable, and the vendor doesn't have to deliver the LGPL libraries because they're already in Syllable. But if you are making applications and you want to use libraries in your applications, then the situation is different, because if you need to bundle extra libraries with your application, and those libraries are LGPL, then you must offer the source code of the third-party libraries that you bundle with your application. And we in open source tend to think that that is a very small requirement for getting the benefit of entire free libraries. But the thing is that commercial software vendors don't like this. And some of them go as far as Apple does in their App Store. They do not want GPL, they do not want free software in their App Store, not even LGPL libraries that come with apps, because then the App Store is legally obliged to offer the source code to those libraries. And they don't want that hassle. And we think that's weird, but that's the way it is in the world of commercial software. And in the past years we were hoping in open source that open source was winning, and we wouldn't have problems anymore with commercial companies accepting free software, LGPL and GPL. But the point is that we are in a big move to small mobile platforms, and at the moment the leading vendors, operating system vendors in small phone platforms and netbooks, have closed source operating systems, and in many cases they're using an open source lower layer, because almost all of them are building on Linux, and Apple is building on a BSD lower layer. But on top of that they have a closed layer. iOS is closed in the top layers. WebOS is closed in the top layers. Android is mostly open, but people are complaining about it lately because Android is not a really good open source citizen, because you get code drops instead of continuous open source development. So the code for Android is mostly open, but it's not a really good open source project. So all the new big winning open source new mobile platforms are not open source in their top layers. So the pendulum is swinging back to closed systems for the moment being. And we will have to correct that in the years to come, but that will be a very long and slow process to get really open source operating systems on smartphones and tablets and netbooks.
So Apple's App Store does not forbid people to offer BSD licensed programs.
No, that's the point. If you have to bundle libraries with your application, then commercially it's much better if those libraries are under a liberal BSD style license than under a free software license, because then you're not obliged to offer the source code in your app stores. And it's not really a problem for open source, because all those libraries are well known, and you know that the source code is available from the project that makes the library anyway. So in practical terms it's not a problem for open source, but it is easier for commercial app stores if the libraries are BSD. And that's one of the big reasons that Red itself is BSD licensed. And although we have always meant to write LGPL libraries in Syllable, I am now writing bindings for Red that I'm publishing under the BSD license, so that they can be integrated with Red. I could license my bindings LGPL, and then it would be no problem to bundle them in Syllable. But to make it better for Red, to bundle it with Red applications, I am licensing them as BSD. We'll have a look through the rest of the roadmap. Here's your original question about the backends. A number of backends are planned. The first backend is of course for the old Intel x86 CPUs, also known as the IA32 architecture. So that is simply done, although the compiler could always be made more optimizing, of course, but that's something for the future. The goal for Red System now is to have it as soon as possible so that you can continue with building Red. So the fully implemented CPU backend is now x86. So you can see here that the ARM version 5 port has been started, but it's not very advanced yet. And then there are the AVR Arduino boards, the Arduino boards and others with the AVR CPUs. And the AVR CPUs used to be their own CPUs in 8 bits, so that's for very small embedded boards. And Nenat is doing that as a weekend project, I believe. And so it's not a major focus, but most weekends there is some progress on it. So there has been some progress on supporting very small AVR 8-bit CPUs. So that's really a very, very small target. And the interesting thing is that such small embedded systems have very little memory. So it's possible that the full Red language will not be very usable on such small platforms. It's possible that Red will use too much memory in most cases. But that's not a problem really, because we also have Red System, the low-level language. And if you have such a small embedded platform as a target, you have to develop in very efficient low-level languages anyway, usually C or C++. And Red System is an excellent alternative for C and C++. So for such small targets, it's not a problem to develop in a low-level language. And so Red System will be very useful for that. Well, and then the newer, larger AVR CPUs are actually licensed ARM designs. So the 32-bit AVR CPUs are very different. They are ARM processors, but small ones. So they're yeah, I guess they're also ARM Family 5, but I'm not sure. So maybe these two are more or less the same. Number 2 and the AVR 32-bit, they're both ARM. But as I said, the ARM is not really a platform, it's very fragmented. So you have to support different ARM platforms very specifically. So if you're talking about AVR 32-bit ARM, you'll have to do different support than for ARM v5 in general. So there will be some differences between ARM backends. Well, then we get to the virtual machines we talked about. JVM is of course the Java virtual machine. So the same way you could generate Dalvik bytecode, you could generate JVM bytecode, because the Java virtual machine is standardized, but the Google virtual machine for Java, which is called Dalvik, which runs on Android, is very different. So Dalvik is not even here as a target, so it's possible that Nenat is not planning to do the Dalvik backend himself. So maybe Nenat is planning to generate ARM machine code on Android immediately. But other people have said that they are interested in doing a Dalvik back end. So it's probably going to be a community contribution to have an Android Dalvik backend. But the JVM bytecode is an official target. And the CLR, the virtual machine for .NET, is an official target. And AVM, that is the virtual machine for Flash. And AVM2 is version 2 of the Flash virtual machine. And then you're basically talking about the virtual machine for ActionScript. AVM, I suppose that's ActionScript virtual machine. And ActionScript is pretty much a clone of JavaScript. So the AVM virtual machine is basically the ActionScript JavaScript virtual machine underneath Flash. So if you would have an AVM backend for Red, you could also run in Flash. So all those 90% of web users who have Flash installed, you could run on that virtual machine on the client side of a browser. Because if you're generating bytecode for JVM or for the CLR for .NET, you're probably running, if you're doing it in a web browser, you'll be running on the server. But if you're generating code for the Flash AVM engine, then you can run on the client side of a browser in the Flash plugin. Well, and the last official target, that's for the Intel AMD architecture, but the 64-bit version, of course. At this moment, Red is quite 32-bit oriented, but from the AVR 8-bit backend, it is going to support 8-bit CPUs. And that also means that you will have to support some level of 16-bit data structures. And for the 64-bits target in the future, you will have to add 64-bits data types. But as I said, at the moment, the Intel target is the main focus. There is some work being done on ARM and on 8-bit AVR CPUs, but that is still very experimental. Yeah?
The Red project seems pretty ambitious. How many developers are working on it?
We have a project group, if you can call it that, of about 5 people. And I can bring up their names in a while because they're in the thank word for one of the releases. But actually the language itself is developed by Ninat alone. So the core project is just one man, and in half a year we got a C-style language with a runtime for a number of operating systems, and the start of backends for multiple CPUs. And we already have backends for multiple binary formats. That's under here. Here are these were the CPU backends. The machine code backends, but here are the binary format backends. PE-COF, that is the exclusive Windows binary format. And there are a number of features of a binary format that are important to support. It's even more ambitious than I've shown so far, because at this moment Red is a complete compiler. And it's also a complete linker. So the very interesting thing is that you don't need a C compiler, you don't need a C++ compiler, you don't even need a standard linker, because Red does the linking itself. It from back to front, from top to bottom, it generates the complete machine code and the complete program executable by itself. So, for example, people have always wanted a developer version of Syllable releases. and there have been ones years ago, but the problem with the developer version of Syllable is that the operating system is quite small, but the complete compiler tool chain from the GNU project is very large. And a developer release of Syllable will be at least twice as big as the normal releases. And if everyone is going to download the full release, our downloads, our traffic is going to double. And it's only important for developers, but chances are that everybody is going to download the full version. And it's extra work, so maybe 5 years ago some people once made a developer release, but the hosting was a problem. It wouldn't be as big a problem now as it was then, traffic-wise. But at the moment we simply don't have time for an extra developer release. And the interesting thing is that right now it's possible to integrate Red into Syllable Server, because Syllable Server already includes Rebel 2. And after the bootstrap we can easily include Red in Syllable Desktop, and it's tiny, it's just a few hundred kilobytes, and that's mostly the test suite. Red itself is something on the order of 130 kilobytes at the moment, and that does the same work as the GNU toolchain with GCC and the binutils, the compiler and the linker, which is by now somewhere around 50 megabytes, somewhere around the same size as Syllable itself. So instead of those 50 megabytes of GNU stuff, we will add Red to Syllable, and that will increase the download by a few hundred kilobytes, and then you have basically the same functionality as with the entire GNU toolchain, without having to double the size of the download. But because Red is a complete compiler and linker, eventually you will want to have the support of all the things that compilers and linkers do. And at this moment the Red compiler and linker only generate program executables. But eventually you will also want to write your libraries in Red. At this point you can generate Red program executables, and they can load other libraries. Those are two features. Feature 1 is basically the ability to generate program executables. Feature 2, the imports, is basically the ability to load other libraries. And those other libraries can be written in other programming languages. So in a Red program you can currently load libraries written in C and in other languages such as C++ if you have a proper interface for binding. But the third feature in this list, PIC, that is position independent code, that's what you need to generate libraries. So PIC is not implemented yet, and when we get that we will be able to generate Red libraries. So then you will be able to write C applications or C++ applications, and in those C++ applications you will be able to load libraries written in Red, the other way around of how it's done now. And then there are a few more forms which your libraries can have, really. PIC is the first step, and then you need shared library support. So step 1 and 2 were necessary to generate executables and load other libraries, and step 3 and 4 will be necessary to be able to write libraries in Red. And then step 5 and 6 are a bit more esoteric. Those are alternative forms of libraries that are useful when you want to link your libraries in different forms than a shared library. A shared static library is necessary if you want to link Red libraries statically, So with step 4 you can have a separate red library that you have to bundle with your application, and with step 5 you can link your red library into your C++ application or whatever, so that you get a single executable, which is very nice for distribution if you don't need other files. And then the object format, that's really a low-level intermediate format that's nice for very deep linking ability, but those are all lower priority. This is ordered in priority, and the next step is to support red libraries, step 3 and 4. So this is all being done in priority order. And the executables and library loading have been implemented for the Windows PE format, and after that they have been implemented for the ELF format, which is used by most open source systems. So that was the Linux support. And then there are some details in the formats that needed to be changed for Syllable Desktop. That has also been done. It's not mentioned here because they're details of the ELF implementation. And then there's the Mach-O format, which is the exclusive format of Mac OS X. So it was also necessary to implement that separate format to support Mac OS. And that's also been done, including loading shared libraries. And the interesting thing is that after that Nenad reported that when implementing this, it turns out that the Windows PE format is actually the simplest to support. And the Apple Mach-O format was the most difficult to support, the most complex. And the important goal of Red, to be able to cross-compile, was almost impossible on the Mach-O format, on Apple OS X, because it's a very strong strategy of Apple to require that if you want to develop for an Apple platform, even for the iPhone, for iOS, that you need to do that on an Apple machine, on an OS X machine, in the Apple Xcode development environment, the development IDE even. So Nenad needed to make some special arrangements in the support for the Mach-O backend to circumvent that, and to make it so that you can still cross-compile to Apple. So it's really a rather special feature that Red can cross-compile to OS X without needing an OS X machine. It was almost sabotaged by Apple. But it was a political reason from Apple, not a technical reason. Well, you don't know. They can always deny that, of course, but it's quite clear that Apple wants you to develop on a Mac. If you want to develop for the iPhone, you need to do that on a Mac in their Xcode IDE. And it's clear that they don't want you, they don't like you to use other systems. And what Microsoft has also always done to create a barrier for others for Windows development, it's very easy to let some technical details slip so that it can't be done otherwise. It's very easy to slip some technical details in your